Good afternoon. I'm here to talk to you guys about Halite halos. My name is Zane Cable, and let's get into it. So, for some background, we're going to talk about one of the more powerful models for dark matter that we have going right now. It's called the WIMP model, weakly interacting massive particles that are electronically neutral and don't interact with the electromagnetic spectrum. They're very stable. And they only interact with other matter with weak force and gravity. They are outside of the standard model for particle physics. Some benefits that we get from using this model, though, is that it provides a very natural explanation for the progression of certain events that we've seen, like gravitational lensing, rotational curves of galaxies, etc. Another factor is that if they follow this particle model, then they will be detectable either directly through the interactions with matter or indirectly through annihilation and decay. So we're mostly going to be thinking about the direct interactions for a lot of what we're going to be talking about. Now, modern detection, like the ice cube or the DAMA, they use these really large-scale laboratories in which they have these really, really big detectors to get a really large area cross-section for their exposure. As you can see in the formula for the exposure down there, the area and the time are very big factors, as well as the work function. But since we're all looking for the same kind of dark matter, it's all about getting that right optimization of area to time. So the ice cube, they operate with these giant tubes that go deep down into the water. And when these the samples inside these tubes are hit with these neutrinos or other particles of similar energy ranges, they interact with the nucleus inside the detector, and they emit a particle that is detected as light from these detectors on the top. Well, the DAMA uses sodium iodide with titanium to modulate signature over each year from the flux of us moving through the galaxy. Paleo detectors are going to go for the opposite end of this spectrum. So instead of trying to go for a really big area with a live time detection, by the way, the ice cube and the DAMA have been going for about 15, almost 20 years now. So their time exposure is about 15, 20 years in comparison to their area, which is like kilometers, really, really large scale. Over here, though, paleo detectors offer up to a gigayear in time scale with areas very small, though. And the concept is we're taking these minerals and rocks and other things from the Earth, and we are going to analyze the interactions these particles have had with them over the past billion years. The sensitivity of these is just simply better than the other experiments right now, as we can see. So for like a low mass of dark matter, low mass particles for dark matter, we estimate that we can see less than 10 giga electron volts. The cross sections would be magnitude smaller than the current limits. High mass above 30 giga electron volts, we're about 1 to 100 times smaller than the current limits. Both of those things are very good. We want to optimize and get those cross sections to be as optimal as we can so we can parse as much data as we can. Just the amount of exposure that we are capable of getting with those large time frames, despite the small area size, is really phenomenal. It is a challenge to reconstruct the nanoscale damage features, though. Anything less than 500 nanometers is there's always challenges to get those operations to be functional. So one of the things that causes those challenges with those nanoscale things is backgrounds, because there are so many things that could be causing those similar size scales at that level. Now, noise sources, these are things that are noise, things we want to eliminate and what they are caused by. So like the cosmogenic sources, cosmic rays, neutrons that are caused from muon interactions in the atmosphere, those are very damaging and the similar energy range to what we're looking for. We can reduce those by getting samples that are deeper than about 5 kilometers. Just below 5 kilometers, the amount of interactions from those is reduced to less than a 0.01 parts per billion. The deeper the sample, the less cosmogenic interactions you're going to have to worry about. Now, radiogenic is from the uranium 238 that is throughout the Earth's crust and a whole lot. And there's also alpha, beta, and gamma decay mechanisms that we also have to worry about from radiogenic sources. We can help with that by taking our samples as more radio pure samples, things with less radioactive isotopes present within them, or that form away from higher density regions of uranium. Now, neutrons, spontaneous fission from uranium. So that same uranium can also, instead of going through the normal alpha thorium decay mechanisms, could spontaneously fission, branching into two neutrons firing out with a pretty high energy. And the range of that is within one of the things we're trying to avoid. But the mass of those neutrons and the in hydrogen-rich samples is mostly deflected within the elastic range. So we don't see a lot of the damage if things are in hydrogen-rich environments. Now, neutrinos from the sun, supernova, cosmic ray interactions in the atmosphere, and other sources are still a big noise concern, but that's okay because we also want to find out more about neutrinos. We're still looking for more and trying to discover more about their interactions as well. So we're happy to see neutrinos. We're working on methods to eliminate them as well in the future. Now, halite is the material we have selected for the course of this project. Halite can be mined at least a depth of 5 kilometers so we can get rid of that cosmogenic radiation. It's a mineral evaporate, and the formation and process of it is very radio pure. It's just sodium and chlorine with very little imperfections of stuff like that. Now, it's found in hydrogen-rich environments. It is a mineral evaporate, so it forms near water or silt, soil, rock caves, stuff like that. Can help form a salt, and so that helps it prevent the neutron interactions. Now, we have demonstrated before in a previous thesis that it has the ability to retain tracks. We've found tracks within them. These tracks that I'm referring to are damaged tracks caused by these weakly interacting particles, such as neutrinos, or even some of the noise sources as well. We've just proven that you can see tracks, and we are still working on refining which tracks we can see. Another thing about it is that it is etchable, and we have defined a pretty solid etching rate. The fact that it's etchable helps tremendously because we can take those really small nanoscale, half a nanometer, like angstrom size interactions, and we can blast them to 100 times bigger, even more than that, with some plasma, which is our strategy. We'll get into that later. And preferentially etch those little defects that are caused by those interactions into forming larger, more optically observable information that we can then retransform back to the original energy and get back the information we want. Another big part is that for our tools that we're using for analysis, our samples have to be relatively flat so we can scan over the surfaces really well. And halite is really good at that, as it is cubic and has a very nice cleavage planes. So we can get good flat resolution so we can zoom in really close. So the average procedure it takes to prep some of this halite, we would take a block of it, we take a little rock hammer, and we would cleave a section off of it, relatively thin. Now, we then take that sample and we optically observe it for general flatness. We're looking at the cleavage plane, and we're looking for just standard defects and other things that we can note on the surface. We take a couple images, and then we're going to put it in the plasma etcher. We're using a sputter system. Right now we're using argon with 100 watts, 10 minutes at 0.2 H-bar pressure. And so in there, it's going to go in. The plasma is going to kinetically attack these regions on the surface such that it will destroy preferentially the more defect-rich areas, such as these nuclear recoils. Now, after that, we take it over to the laser confocal microscopy, and analyze it for surface profilometry. Now, we'll get into that in just a second. And then the code. The code is for the image processing of the images we're going to get from the LCM. And we'll get into all that in just a second. Now, etching. Let's talk more about that. Calculations for etching rate we did, and my predecessor calculated them to be about 14.47 nanometers per minute. And that's with the current ranges that we're doing. That's the 10 minutes, 100 watts, 0.2 mbar. And as you can see here in this cartoon, a nuclear recoil track. Those are the etch pits. So as it gets ablated by this by the plasma, those are going to preferentially become more rounded, and it's going to hit those surfaces much harder than it's going to be hitting the sample surface, which allows us to get images like you see in the top right here, where you can start to see the actual tracks and the inertias of them based on their angles and trajectories. Now, let's talk about the meat. So the halo here, this is the anomaly that we found during what I was previously discussing our processes. So this halo was just observed and imaged in one of our samples, and we think we've talked about this a lot, and we have decided that it is most likely during formation of this halite sample, there was a small fluid pocket that had radioactive particles, probably some uranium dust, that decayed. And over time, it started to create this little halo, this circular feature you can see here. And the important part here are these little pits that form this circle here, which would be the slight stochastic nature of decay for what we are presuming right now to be alpha particles on the final interactions during their trip through it. So the stopping range in the material. Our goals are to discover what we can about the alpha damage tracks from observing that ring of dots. Decrease the error on our etch calculations. So since this is a three-dimensional artifact, if you will, we can decrease the error on this etch calculation by etching the same sample with the halo further and then checking the radial change. So from the center where the fluid was trapped, there is a sphere around it of these pits. We just happen to bisect it. But that sphere has a changing radius as we get deeper and deeper and closer to the edges of it. We can use that change in radius to get a way more precise etching rate. And then we would like to discover other halos. So that's what the code is all about. We're doing a halo search. We're going to be chopping and etching a whole bunch more halite in order to try and confirm other halos. And if we do, and if we are able to find more, we'll be able to determine their origin and get a more precise answer to all of our questions. Now, the LCM, the tool that we're using to analyze all this, laser confocal microscopy, is a phenomenal tool with incredible resolution in the Z direction, so we can get really, really good profilometry. Now, that's necessary for what we're doing with these etch tracks because they're so small. With this, we are zooming into about 50 times, and we are getting a bunch of images of a whole sample. We can scan it across the whole thing. It takes a little bit of time, but all things do. Now, the image density. So the images that we get from each section at the 50 times zoom are approximately 1,000 pixels across and 800 pixels down. So, about 800,000 pixels total. One sample is about 11,000 images, plus or minus 5,000 based on sample size. And what that means is that when we're running our code, it's going to have to raster across each and every pixel and each and every image. We'll get into that in just a second. So when we analyze each image for this code, we want to establish first an inner and outer radius that it's going to probe. And when it probes, it's going to calculate the roughness between those radii. And the radii are determined by that first halo that we saw. And we are starting with that simply because, like I said, we had perfectly bisected it. So that is the maximum radius of the sphere of influence. Next, after it calculates the roughness within that region, it's going to translate that those radii, those circles, over X number of pixels. We're working on the optimal ratio of how many pixels we can skip. And then it's going to repeat. It's going to calculate that roughness again, and it's going to create an array at each location. And then after we have that array of roughnesses, we're going to group those by magnitude. And so a section of roughness that matches with others is going to be very rare. Most of the roughness is going to be just completely random, just a bunch of numbers from little ticks and tracks all over the place. But if we see a big, large increase in one of these group roughnesses with a like 2 or 3 confirmations as it goes through the pixels right around it, then that tells us that there is a halo there. And we can take that information and we can use this and apply this to hundreds of samples, thousands at a time, run this, and we can try and find more of these halos. So using what we have access to, we have discovered this anomalous defect within the halite. And analyzing that is going to help us get a better interpretation of the characterization of the damage tracks present within this mineral and others. We aim to prove that this source, the source of this anomaly, is what we think it is right now with uranium-238, based on some other techniques such as SRIM calculations, where we can check the stopping range of matter and interactions within it. So, for instance, as the uranium decays, it releases that thorium and the alpha. The ratio of the tiny pits closer to the center of our ring and the actual pits that we're looking for should fit that SRIM calculation towards those distances. If that ratio is correct, then we have shown that it is in fact uranium-238 to a high degree of certainty. Next up is the characterization of these halos. It can help us better refine our background data, and therefore, in the context of paleodetection, a better resolution and understanding of the background interactions of alpha decay and the thorium, as well as the other implications of the halo, are all very important, so we can get more and more refined in our modeling, as well as in our details and our data that we're able to produce. One step closer to dark matter is a big step, and that's all we're trying to make. That is all I have for you today. Thank you so much for listening and for your patience with my stuttering. I hope you have a great night.